morning, friends. I am Dr. Dwivedi, professor from the Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. It gives me immense pleasure and joy for my lecture series on engineering thermodynamics. As of now, I have completed module 1. In that, I have discussed about the pure substances, zeroth law of thermodynamics, work, heat, energy, first law of thermodynamics, limitations of first law of thermodynamics, number of numericals we have already solved. In the second unit, which is second law of thermodynamics, we have started with statements of Kelvin and the Planck statement, which relates to the heat engine. And the second statement, which is from the Clausius statement, which relates to the heat pump and refrigeration and air conditioning. Further, we have seen that the absolute temperature, how to find the absolute scale of the temperature. Then we have seen the Clausius inequality, in which the cyclic integration of del Q by T should be less than or equal to 0 for any working cycle. If it is the 0, del Q by T is 0, it is a reversible cycle. And if cyclic integration of del Q by T is negative, it is irreversible cycle. At no case, del Q by T, cycle integration of del Q by T should not be greater than 0. So this statement is given by the Clausius, and this is known as the Clausius statement. We have also seen during the statement about Maxwell demons, in that we have some limitations of the first law, that there is a friction, there is a expansion, free expansion, that is mixing of the gases, or some eddy current and other things, eddy losses. This is making the first law of thermodynamics to the second law of thermodynamics, because the first law of thermodynamics doesn't say about how much percentage of heat if you supply will be converted to the work, or how much you give the work, how much heat it will be extracted. It is not explained. It doesn't say. It is saying about the del Q is equal to del W for any reversible cycle. But in the real scene, it is not happening. The objective of all of us here as a scientist or engineer, the first year or the second year, we should start here learning the concept of, here it is very good concept, because here in the irreversibility, it gives that how much we can improve so that we can reach to the reversible. The Carnot cycle says that the efficiency of any reversible cycle, eta, is equal to 1 minus TL by TH. So, this is neta of Carnot is equal to 1 minus TL by TH. So, if this is the TH, this is the TL, and there is an engine, this gives the work. So, this Carnot cycle, TL by TH. So, it says that how much this value is less, how much TL by TH is less, that will be, efficiency will be high. So to have this TL by TH less, TH should be more or TL should be less. I am giving here the very good concept for all researchers and students. Not only you should learn for your examination point of view, you should learn your knowledge, your concept, basics. So if you want to design the engine, so what you have to think, your efficiency should be high. No engine we can make which efficiency is more than the Carnot cycle. So understand that in which temperature range we are working. So how we can find out that what is the temperature range? Mostly our TL will be the atmosphere where your exhaust is going. Maybe in the summer it may be 45 degree or 50 degree. In winter it may be 10 degree, 5 degree, 8 degree, 20 degree and so on. So means it is from 0 to 50 degree. That is your TL always. But what is the TH? Till now we have discussed so much thing about TH, but in fact, if you take the engine, in the real engine, you take the car engine or the bike engine. Inside the bike engine, we are putting some fuel. And this fuel is burned. So how much temperature that fuel burned is releasing? That temperature is the TH. TL, you know. So that temperature, maybe 1400, 1500 degrees centigrade is generated inside the combustion chamber or inside the piston head, above the piston head. That much temperature is your TH and TL. So if you want to increase the efficiency, so either you increase the TH or either you decrease the TL. So in the real case, actually this TL should be the atmospheric temperature. But in the real scene, if you see the exhaust of your gas from your car or your bike is not atmospheric temperature. It is, I think, more than 150 to 200 degrees centigrade. Means if it is 200 degrees centigrade or it may be more than that, that much you are wasting. So your intention should be like that, how I can reduce this 200 to 40 degree or 50 degree or 100 degree. If you are able to reduce 2 to 3 degree by any means, that exhaust is not going at a high temperature. So it means that TH is utilized. Means whatever petrol you are burning, how much heat you are extracting or you are giving away from the engine, that much is your waste. Can you use that heat for the further work? Can you recirculate that heat and it can heat your combustion chamber? Or this heat can you use for some other useful work in your bike or your car? That type of thought we have to develop. Then only we will feel that yes, you are working, and then your concept of engineering thermodynamics will work. This is a basic course for mechanical, for the aeronautical, some chemical engineering or some other people. But those who are working for the research, a very basic concept has to be developed for this process. So in today's lecture, I gave some just brief of why we need to learn this all entropy, because entropy is a loss. Our objective is to reduce this entropy as much as possible. If you are able to reduce this entropy, that much efficiency, that much fuel consumption, that much pollution in the environment you are able to save. That much energy you are saved, that much money you can save. Okay, so it is very nice, interesting issues, and that we have to understand. In today's topic, I am going to discuss about principles of entropy increase, entropy generation, statement of increase in entropy principles, availability and irreversibility, decrease in availability when heat is transferred. These are the topic which I am going to discuss today, and I will just go for further the previous lecture which I have taken just before that. derivation of the entropy equations, we have seen that delta S is equal to, we have seen for the incompressible or for incompressible materials like solid and the liquid, delta S is equal to CV ln T2 by T1. This is for the incompressible material. Then ideal gas, we have seen that delta S is equal to CV ln T2 by T1 plus R ln V2 by V1. This we have derived, and also in other term also we have find out. So this we have already done it. Principles of entropy increase, we have already done on how these things are increasing. Gibbs equations, we have already find out that TdS is equal to U plus PdV. Third law of thermodynamics also we have discussed in our previous lecture. Entropy of solid, liquid and the perfect gas, we have already derived. Entropy of principles of entropy increase. Okay, so this we can see here that principles of entropy increase. First we will see about non-flow processes. So we know that by the Clausius inequality that the following cyclic integral is always less than or equal to 0. So we have seen, I think you remember that del Q by T is always less than equal to 0. This is the Clausius inequality statement. The Clausius inequality that the following cyclic integral is always less than or equal to 0. So less than or equal to 0, or it is minus or it is 0. These two things should be there for a reversible cycle. So if it is the 0, it is a reversible, and if it is a minus, it is irreversible cycle. This so here the Clausius inequality, it is del Q by T less than or equal to 0. This we have discussed in very much detail, and last two classes we are discussing about this cyclic integration of del Q by T is less than or equal to 0. This leads to the definition of the property called the entropy. We have seen that del Q by S is equal to ds. So del Q is equal to T into ds. Considering now an irreversible cycle in which process 1 is greater than or equal to 2, follows an irreversible path, and process 2 and 1 is a reversible path as shown here. So here 1 to 2 is a irreversible and 2 to 1 is reversible path. So here we can see that cyclic integration of del Q by T is equal to 1 to 2 irreversible del Q by T plus 2 to 1 reversible del Q by T less than 0. Okay, because it is one reversible is there, so it will be less than 0. Now, if you see for another process, that is 1 to 2 irreversible del Q by T plus 2 to 1, this is the ds is equal to 1 to 2 irreversible dq by T plus S1 minus S2 is equal to less than 0. So this S we can write S1 minus S2, and this is the irreversible process. So here this delta S, S2 minus S1 will be always greater than del Q by T. So here we got for a non-flow process or the control mass process, the change in delta S will be always greater than or equal to 0. This for the adiabatic process, del Q is equal to 0. So this will indicate that for delta S is equal to or less than 0 for other processes. But for the adiabatic, delta S will be always less than or equal to 0. Either it will be positive or it will be 0. It will not be negative. That we have to, for the non-flow process, we have got that the del S is equal to or greater than or equal to 0. This we have got for one process. Here it is, process is depicted here. This you can see here, that here is the point 1. This point you are going first with a red line, which is the irreversible process, and then it is reaching to the 2. From the 2 it is going to the reversible process, reaching to the 1. So this 1 to 2 and 2 to 1. So it is here that if any one process is reversible, your system will be irreversible. Okay, so here if it is any one is irreversible, your delta S will be always greater than or equal to 0. So always delta S should be positive. If you are getting any answer, you are calculating and you are getting the minus, means there is some issue, you are not considered the sign properly. So now we will see about the entropy generation, okay, how this entropy is generated. The entropy change of an adiabatic process is always greater than or equal to 0. Just now we have seen that delta S should be always equal to 0. It means it should be positive or 0. For reversible process, it is 0, and for irreversible process, some positive number should be there. Where the equality applies to the reversible process, if the equality applies to the reversible process, here just you can see here that if it is a system, this is the surrounding T naught, so Q surrounding is minus Q. So the surrounding, because it is going from here to here is a plus Q, but surrounding is a minus Q. However, not all processes are adiabatic. In the real life, we will not see that all processes are adiabatic. Nevertheless, we can always enclose a system in a surrounding environment which is adiabatic. So if you surround with the surrounding, then this system will become the adiabatic. Thus, considering the total entropy change of both the system and the surrounding, if you consider the total entropy change for the system and the surrounding, we will get S total is equal to delta S of the system plus delta S of the surrounding. So delta S of the system, and this is the delta S for the surrounding. So this is here given. So here this we can write this delta S of the system plus delta this Q surrounding by T naught, because this is the adiabatic. All the surroundings are adiabatic. So this delta S system plus Q surrounding by T naught is equal to greater than or equal to 0. So entropy generation. So entropy generated Sgen is equal to delta S total here. S total is equal to delta S system plus delta this Q surrounding by T naught greater than or equal to 0. Here Q surrounding is a minus Q. So here, if you see here that dividing by M, you will get S generation is equal to delta S system plus Q surrounding by T naught equal to or greater than 0. So this is called S generation. So this S generation will be always in the positive direction. Positive number will come here. So it is called the entropy generation. So now statement of increase in entropy principle. So what are the statements and how we can consider this aspect of entropy generation? Thus, the increase in entropy principle states that for any process, the total change in entropy of a system together with its enclosing adiabatic surrounding is always greater than or equal to 0. This total change of entropy is denoted the entropy generated during the process. So always the entropy generated for any process of a system and the surrounding is always greater than or equal to 0. So S gen equal to 0. This is the principles of increase in entropy. This means that always S generation will be positive in the real sense. This total change of entropy is denoted by the entropy generated during the process, that is S generation. The unit of this thing is kilojoule per Kelvin or kilojoule per kg Kelvin. So if it is the specific entropy, it is specific entropy, and this is only entropy. So it is per kg, it is for the mass. Now I will discuss about availability and the irreversibility. We can see that in the nature we have so many sources of energy like ocean, your air, your rivers, solar energy. So many natural energies are available, but how much we can extract from this, that is the issue. So availability and irreversibility, most of the systems in our nature are irreversible. The same thing will not happen. Irreversible means it should go to the state and it should reach to the same, the system and surrounding should reach in the same position. I will give one example here that if this is the your one and there is a one block here. This block you are moving from here to here. So during this motion, due to this friction here, some energy it is gained. Now this is the 1 to 2. Now again you back again from here to here and you are putting here the same thing here. So now it is, assume 1 plus. Now if you again you go here, this will have 2 plus energy. Because during the returning also it is taking some friction and it is due to air friction, due to the ground friction, it will generate some energy. So here the extra energy is there. It started with 0 energy here, but when it is reaching again here, it has got 2 energy. It is not a reversible process. Reversible process means the process in which the systems and the surrounding should have the same status as it is reached. So now what we have to do? We have to release this 2 plus energy to the surrounding. So the system is now in the same state, or it is a same state, but surrounding is not. Surrounding is not in same state. So this it is internal, it is reversible, but externally it is irreversible. So like these systems are reversible and irreversible, and this we are going to discuss here, availability. And here also we will see that how much percentage of our energy we can use from the nature. Okay, so that we are going to discuss. So this availability is also known as exergy. How much percentage of energy you can get from the resources. So when a system is subjected to a process from its original state to dead state, the maximum amount of useful work that can be achieved under ideal condition is known as available energy or availability or exergy of the system. So when a system is subjected to a process from its original state to the dead state, the maximum amount of useful work that can be achieved under ideal condition is known as the available energy or the availability or the exergy of the system. So we may have a huge amount of, if you see the ocean, the energy of heat Q is equal to mCV dt. So this temperature, assume that 40 degree, and mass is huge. So the energy available is so much that whole world can enjoy. If you see the solar energy, so much energy is there. But how much we are able to use for the useful work? So how much energy we can use for the maximum amount for the useful work? That energy is called the ideal condition, and this is known as the available energy or availability or the exergy of the system. So here we can see that we have here the one heat engine. It is at the so T1, then Q1 heat is absorbed from here, going to the engine. This is the reversible engine. Maximum work is produced by the reversible engine. So this is the availability energy. This is called energy available in the system. And the Q2 is released. This is unavailable. This is going to the surrounding. And this is the T2. So how much is this unavailable and how much is the available? That we will see here. This work done, if you see the TS diagram from X to Y, from point 1 to 2, this is QXY. Here from here to here, it is available in this block, which you can see this hatch line. This is the available energy, and this is the T naught is unavailable energy. It is gone to the surrounding. So this is called the exergy or available energy or availability of the system. So in this way, available and unavailability of the energy is expressed in this way. So here, if you see, maximum work done is equal to available energy, and this is the QXY minus T naught SY minus SX. So this much energy is waste. So this is obtained QXY. This QXY is energy which is total energy here. In that, this much energy is wasted. So available energy is equal to total energy minus waste energy. So this is called the available energy, and this is called the exergy. Now, available energy and irreversibility. So as of now, we have seen the availability or exergy. So how much we can use, the maximum work producing energy is called the available energy. But how much is the waste? So unavailable energy, we have seen in the previous one that T naught SY minus SX. So here Sx and Sy are the entropy and at X and Y respectively. And this we can see that the available energy is also known as exergy and unavailable energy as energy. Okay, so the energy which is not available is known as the energy, but which is available to do the work is called the exergy. The energy which cannot be utilized for doing work is called the unavailable energy. Now, irreversibility is equivalent to energy destroyed. So, what is the meaning of irreversibility? Irreversibility is equivalent to energy destroyed, hence also known as the energy destruction. Consider the example below. This you can see here that how we can see this in this. This is the total energy Q. This is the available energy. This is the unavailable energy. From the available energy, this is the work output, and this is the irreversibility. This is the irreversibility. Okay, some energy will be wasted by this. So, total output, if this is the total energy available, some work is we are getting exactly, but there will be some losses. These losses are indicated by this irreversibility effect. So, in this way, we can get it. Next point is decrease in availability when heat is transferred. So, how much available energy is decreased during the transfer of heat from source to the sink? How much work is produced? These are things we are going to discuss here. So, consider a reversible heat engine operating between the temperature T1 and the T0. Here, this you can see here that this is 1, 2 is the at the T1 temperature, and in this, if you see, this is the your waste. Okay, so now if you see here that the Q1 at state 1 is equal to T1 into delta S. So this work done is equal to available energy is equal to T1 minus T0, T1 minus T0 into delta S. So this energy, just I will put here with some other color. I am putting here. This is the your work done or available energy. So this is the, I will write available energy. Okay, so work done is equal to available energy, and this is the T1 here, T1, and this is the T0. So T1 minus T0 into delta S. I think this is very much clear. Let us now consider heat. Q1 is transferred. So now this Q1 is equal to T1 into delta S. So now the next one is T1 prime, it is transferred, and now it is not in this position but in this position. So here T1 into delta S prime here. This is the delta S prime. So now here delta S prime is greater than the delta S. So now Q2 is equal to T0 delta S. That is the initial unavailable energy. That is T0 into delta S. This one was initial unavailable. This is initial unavailable energy. But now Q2 prime is equal to T0 delta S. So it is a T0 here and delta S. So this here Q2 prime is greater than Q2. So Q2 prime is greater than Q2. So W prime is Q1 minus Q2. So it is less, and this is additional entropy generation. This is S gen. This S gen is done, and during this heat transfer, the entropy is generated. This much entropy, we can say that this is, this energy is additional entropy, and this much heat is lost. This much S is additional heat, is this entropy is generated. This much efficiency of the system is lost. So that is the objective of understanding the decrease in availability and the heat is transfer. So when you heat transfer, there will be some generation of the entropy. This shaded part I have mentioned, this much extra entropy is, this is delta S. This is delta S prime minus delta S. This much is this one. This is generated. And so here the W will be Q1 minus Q2 prime, and this is less than W. This W prime is less than W, which we have got from here. And this is, so in this way, for any heat transfer, there will be some irreversibility. This irreversibility will cause the system to create the entropy. Some additional entropy will be generated, and this generation of entropy will give some additional losses, and work will be reduced. The efficiency will be reduced. So here we can see that the W prime is equal to T1 delta S prime minus T naught delta S. So W prime is equal to T1 prime minus T naught into delta S. So here this W is equal to T1 minus T naught into delta S. So this T1 prime, just you can see, this T1 prime is less than this T1. So here W is greater than W prime. Okay. And how much loss? This loss is T naught into delta S gen, or T naught into delta S prime minus delta S. This much loss is there in the system. Hence, increase in available energy, and the shaded portion represents an increase in unavailable energy. So this much energy is unavailable for doing the work. Next topic, I am going to discuss about thermodynamic potentials, Gibbs and Helmholtz functions, Maxwell relations. So this I am going to discuss in due course of time. My next lecture will be some thermodynamic potentials, Gibbs and Helmholtz functions, and Maxwell relations. These are my references, which are Eunice Senegal, Michael A. Bowles, Thermodynamics and Engineering Approach, Tata McGraw-Hill's 7th edition. And this is the NPTEL lecture from Dr. D.P. Mishra, IIT Kanpur, Department of Aeronautical Engineering. You can refer this. There are so many other lectures also. Any questions, any queries, you can ask me to my email yddwivedi@gmail.com. You are welcome to ask any queries, any questions. Also, I request to like and subscribe this video. Thank you for joining. Soon I will be going for the next lecture. Till then, goodbye. See you. Shabba khair.
Like, share and subscribe. Hit the bell icon for more updates.